In this video, we'll be focusing on chapter of electrochemistry, which is chapter 17. So let's first begin with a discussion of what are electrochemical processes. So some of this might sound familiar to you guys already because you have studied a little bit of this in General Chemistry 1 course, but we are going to discuss a lot of these oxidation reduction reactions in a lot more detail in this course. So let's begin. Electrochemical processes are oxidation reduction reactions in which either the energy is released if the reaction is spontaneous, so that energy is converted to electricity, or the electrical energy is used in the case of a non-spontaneous reaction. So essentially all the oxidation reduction reactions are electrochemical reactions. They can be spontaneous, non-spontaneous. In case of a spontaneous reaction, energy will always be released and it will be converted to electricity, meaning these reactions will happen by themselves. We do not have to supply energy from outside. And in case of a non-spontaneous reaction, energy has to be supplied from outside. And since these are electrochemical processes, that energy is usually in form of electrical energy. For instance, you can see right here one of the examples for a reaction, which is magnesium metal here reacts with oxygen to produce magnesium oxide, or in this a lot of times this is also referred to as a redox reaction, which is an abbreviation for oxidation reduction reactions. Redox means red comes from the reduction and ox comes from the oxidation reaction. That's why these are called redox reaction. Whenever there is a redox reaction, there has to be some compound or element that is getting reduced and another element has to get oxidized. So these reactions cannot happen independently. If there is an oxidation happening, there has to be another reduction reaction happening at the same time. So if this is a complete redox reaction that is happening, we can divide this reaction into two half reactions. These are called half reactions. Why? Because you're essentially just dividing a complete reaction into two separate reactions. That is why they are called as half reaction. One of those half reaction is the oxidation half, where we are showing the oxidation reaction. The other reaction is the reduction reaction. Okay, so for instance, in this case, magnesium reacts with or magnesium oxidizes to form magnesium oxide. So what is getting oxidized here? Magnesium is getting oxidized to magnesium 2 plus, and oxygen on the other hand is getting reduced to O2 minus. How can you identify which is what is getting oxidized and what is getting reduced? Let's look at that definition real quickly, and I'll come back to these numbers that you're seeing on top. We'll come back to that. But let's first define what is oxidation and reduction. So loss of electrons is always oxidation and gain of electrons is called as reduction. It can also be, to easily remember this, you can remember Leo the lion says grr, meaning LEO stands for loss of electrons. L is the loss and E here is electrons. Loss of electrons is called oxidation, meaning O. GR essentially means gain of electrons is reduction. So that makes it easier for us to remember what is what. Now, whenever something is losing electron, the other has to gain the electron. So that's why these reactions, in order to make them complete, one substance has to be oxidized, the other has to be reduced. And how can you identify? One is in terms of the electrons, which is loss or gain of electron. The other is in terms of oxidation number. What you see right here, ON, is the oxidation number. Oxidation always results in an increase in the oxidation number, while reduction always results in the decrease in oxidation number. So that's easy to remember. Oxidation increases in oxidation reaction and reduction reduces the oxidation number. Now, another definition here is oxidizing agent and reducing agent. Oxidizing agent, if you think of the definition logically, oxidizing agent means it's an agent that is oxidizing something. Okay, so what does the oxidizing agent do? Oxidizing agent is oxidizing the other substance. So what is happening to this? It by itself is getting reduced. Okay, so that's where the definition kind of gets confusing. So you have to be very careful with the terminology here. Whatever is getting oxidized is reducing the other substance, right? Because one is getting oxidized, the other is getting reduced. What is a reducing agent? A reducing agent is an agent that is reducing something. So by itself, it is getting oxidized. So when a reducing agent gets oxidized, it is reducing the other substance, right? Okay, now what is an oxidation number exactly? So you guys have already learned a little bit about the oxidation numbers beforehand, but we'll go into a lot more details. There are a set of rules that we are going to follow to identify what is the oxidation number of a particular element in a compound. Okay. Now let's talk about what exactly is an oxidation number. Oxidation number is the charge that an atom would have when it is present in a molecule, or if it is an ionic compound, when all the electrons are completely transferred. So for instance, if we have a compound NaCl, okay, so in this case, oxidation number would be whatever is the charge if I break this compound apart and I transfer all the electrons and convert everything into ions. What would be the charge on sodium and what would be the charge on chloride atom? Okay, so chlorine atom. So in this case, we know you guys have seen this, a very easy example. Sodium chloride would break apart to give us sodium ion and chloride ion, right? So whatever is the charge on each of these ions, that would be the oxidation number for the respective atoms. So for instance, sodium would have an oxidation number of sodium would be +1. Oxidation number of chlorine atom would be -1. It's as simple as that. So certain compounds is fairly easy like this. When we are talking about ionic compounds, we can break them apart and identify what is their oxidation number. Straightforward. Certain compounds, on the other hand, are a little tricky for us. Okay, so let's say, let me give you one example which comes later on in your slide. If I give you an example of a compound like sodium phosphate, and I ask you, can you tell me what is the oxidation number of phosphorus atom in this particular compound? So certain compounds like this are easy to break them apart and identify what is their oxidation number, but for certain compounds it's a little more tricky to find out what is the exact charge on that particular atom. So how can you identify the charge on those atoms? We are going to follow a set of rules. I'll show you the rules right now, and we are going to follow those rules step by step. Don't skip any of these steps and make sure you follow these steps in order to get to the exact correct answer that we want. Okay, so what is the first rule? Let's begin with our rules. The first rule tells us that free elements in their uncombined state have an oxidation number of 0. In easier words, that essentially means that the elements that exist in their that are present in their elemental form, if the atoms are present in their elemental form. Elemental form means how they exist in nature. If you are talking about those atoms in their elemental form, in that case, you can regard the oxidation number as 0. For instance, if I tell you how does sodium metal exist in nature, sodium will always exist as Na by itself. How does iron exist in nature? If I take metal, iron piece, how does it exist in nature? Iron by itself in pure form, it exists in nature as Fe. How does copper exist? Copper is a metal which by itself exists in Cu. How does oxygen exist in nature? Oxygen exists as oxygen gas. This is its elemental form. Whenever elements or atoms are existing in their elemental form, in that case, their oxidation number is going to be 0. So here are some examples. Copper, sodium, iron, potassium exists like this. Lead, which is present in our uh, pens, right? Pencils. Those that exist as just lead by itself, Pb. Oxygen exists as O2. Hydrogen exists as hydrogen gas, H2. Phosphorus exists as P4. Some other examples are like halogens. Halogens like fluorine. Fluorine exists as F2 gas. Chlorine exists as Cl2 gas. Nitrogen exists as N2 gas. If I ask you what is the oxidation number of fluorine in F2 gas, this is its elemental form. That's how it exists in nature. So its oxidation number would be 0. How about chlorine in Cl2? 0. How about nitrogen in N2? 0. Okay, so that's the first rule. So if your compound is not one of these, for instance, right, in this case, phosphorus is not in its elemental form, so we know it is not equal to 0. So we move on to the next rule, which is rule number 2. The total oxidation state of all the atoms in a neutral species is equal to 0. So, and in an ion is equal to its ionic charge. So what is the first part of this rule says? It says the total oxidation state of all the atoms in neutral species is 0. So if this is a neutral species, right? How can you tell if something is neutral or charged? A charged compound or a charged element or a charged ion will always consist of a superscript on the right side. Okay, if there's nothing written on the right side, that means it is not charged. The charge is 0. For instance, in this case, the total oxidation state of all the atoms in a neutral species is 0. So if I combine the oxidation number of 3 sodium, 1 phosphorus, and 4 oxygen in this case, the total sum of that should be equal to the total charge, which in this case is nothing is written on the right side, meaning it is 0. So that's what the total oxidation sum of all the oxidation states of all the atoms in a neutral species would be 0. And an ion is equal to its charge. So for instance, if in this case, there's an example, I give you lithium ion, Li+, and I ask you what is the oxidation number of lithium in this case? There's nothing else next to this lithium, right, to cancel the charge. So whatever is the charge of this ion by itself, that would be its oxidation number. So for instance, Li+ would be +1. What is the oxidation number of iron in iron 3 plus ion? +3. Whatever is the charge is the oxidation number. If I tell you what is O2 minus, what is the oxidation number of oxygen in O2 minus? O is by itself, just one atom by itself. So the charge, whatever is the charge, is going to be its oxidation number. I ask you what is, if I give you ion F minus, this is fluoride ion. Can you tell me what is the oxidation number of fluorine in this case? Whatever is the charge of its ion, that would be its oxidation number. So fluorine oxidation number here is equal to -1. Easy, that's rule number 2. Going on to rule number 3, always go step by step. Okay. So as of now, we have no idea what is the charge of sodium, what is the oxidation number of oxygen, what is the oxidation number of phosphorus here. Okay, we have no idea because the rules that we just looked at does not tell us anything about any of those. Okay, that means we have to move on to rule number 3 now. What is rule number 3? The oxidation number of oxygen is usually -2. So most of the compounds, if it's an oxygen is present, regard it as -2, except if it's a peroxide. Okay. If the name says peroxide, that means the oxidation number of oxygen in that case is -1. Otherwise, it's always -2. Most of the times it's -2. Example is H2O2. Oxidation number is going to be -1. H2O2 is hydrogen peroxide, meaning its oxygen would be -1. Most of the times it's -2. So from here, we now know this oxygen would be -2. So each oxygen would have a charge of -2 or oxidation number of -2 from here. Good. Okay. Moving on, that just gives us information about oxygen, nothing else. Okay. Next, we come to rule number 4. The oxidation number of hydrogen in any compound is always going to be +1. Okay, just regard this as a rule. Oxidation number of hydrogen is always +1. There's an exception when it is bonded to metals in binary compound. In these cases, its oxidation number is -1. What are binary compounds? Binary means 2. Bi means 2, right? So if a compound has only 2 elements, 2 atoms present in it, one of those is hydrogen, the other one is a metal, for instance, let's say NaH, where sodium is a metal, hydrogen is acting as a non-metal. So this is an example of a binary compound. If you see a compound like this, where hydrogen is listed at the second in the form, sodium is listed first, or metal is usually listed first. If it is like this, remember oxidation number of hydrogen in this case would be -1. Okay, and in all of the other cases, hydrogen would be always +1. So this is one of the examples of an exception. Okay, usually hydrogen is mostly listed first. If it's listed first, that means it's a +1. If it's listed afterwards, like in this case with sodium, if there's a metal next to it, that means it's going to be -1. Okay, that's rule number 4. That still does not apply to our question of, I'll write down the question right here. It was sodium phosphate, right? We up until now we only know one thing, which is that for our oxygen, just one of those oxygen, it is -2. That's it. If you want to figure out what is phosphorus, we have to figure out what is the charge for sodium as well first, correct? We are solving for phosphorus. Okay, so we still don't know the answer, so we'll move on to our next rule, which is rule number 5. So I'll go through rule number 5 and 6 together. But first, again, remember, you go stepwise. Rule number 5 states group 1A metals are always +1. Group 2A metals are +2. Fluorine is always -1. Okay, what is this? And let me just go to rule number 6 as well. Rule number 6 states in binary metal compounds group 17 elements, which is the halogens, have an oxidation state or oxidation number of -1. Group 16, which is oxygen and chalcogen family, is -2. Group 15 elements, which is nitrogen family, is always -3. So this is giving you the oxidation numbers if your element belongs to this. How can you remember that? If you remember from your periodic table, what are groups? These are called periods. The rows are called periods and the columns are called groups, right? So this first one that you see right here is group number 1. This is group number 2. Group number 1 includes lithium, sodium, potassium, rubidium, cesium, francium. If you see any of these, they would have a charge of always +1. So group 1 will always have an oxidation number of +1. So for instance, sodium. If you find sodium, it's always going to be +1. Okay. Next, group number 2 will always be +2. For instance, if I see a compound with magnesium, I know what would be the oxidation number of magnesium. It's always going to be +2. Okay. Next, the rule said group number 14, 15, sorry, it didn't include 14. It included 15, 16, and 17. How can you identify group number 15, 16, 17? Remember, everything wants to have or reach the inert state of group number 18, right? If you guys remember, I don't know how you were taught this, but essentially group number 18 is the inert gases. They're very happy. They don't want to react with anything, right? So group number 17 wants to attain the state of group number 18. How can it attain that? It has one less electron. How do you do that? 18 minus 17 gives you one extra electron. So it wants one more electron. So they will always carry a charge of -1. Group number 16, 18 minus 16 gives you -2. So these elements would always carry an oxidation number of -2. And we also saw oxygen always has a charge of -2 unless it's in peroxide form, right? But that rule comes before. So you first apply that rule, then you come to this. Next is the nitrogen family, which is 18 minus 15 gives you -3. So this family will always have an oxidation number of -3. Okay, unless listed. Okay, so now we know from this rule, this is rule number 5 and this is rule number 6 combined. That's how what rule number 5 and 6 tells you. Okay, so I'll move back to our rules. The last rule is rule number 7. Sum of the oxidation numbers of all the atoms in a molecule is equal to 0 for neutral compound. If your compound is neutral, everything should total out to 0 and is equal to charge on the polyatomic ion. So if it's a polyatomic ion, the charge will be equal to whatever is the charge on the ion. If it's a neutral compound, the charge will be equal to whatever is the charge on the neutral compound. Neutral meaning it's 0, so total is 0. Let's see how you can apply those rules. We come back to our question, which was sodium phosphate. So up until now, we know oxygen is -2. How about the next rule? The next rule told us that rule number 4 doesn't apply here. We don't have a hydrogen. Rule number 5 tells us group 1A metals are always +1. So sodium here is group 1A, meaning this would always be +1. So now I don't have to go through any of these rules anymore. Why? Because I'm looking for phosphorus. I already know what is the charge of sodium, what is the charge of oxygen. So we can use this to figure out what is our charge of phosphorus. Okay, how would we do that? I'll move on to this slide right here so that I have more space to write it out. So again, I'll just rewrite this, what we just know, Na3PO3. Okay. From here, should choose another pen. Color. So from here I know now, first I knew that oxygen would always be -2, each oxygen, and each sodium will always be +1. Okay, now how can you solve for phosphorus? What is the total charge on this compound? This is a neutral compound, so now I know the total charge is always going to be equal to 0. Okay, so what is the total charge here? 3 sodium. So 3 and each sodium, let me just write in this form right now. So 3 sodium plus 1 phosphorus plus 3 oxygen. Everything is total going to be equal to 0. Okay, let's just plug in the numbers that we know. 3 times +1, each sodium is +1. Phosphorus is what I'm solving for. 3 times each oxygen here is -2 is equal to 0. So we'll solve for phosphorus here. That would give us 3 plus phosphorus plus minus 3 times -2 will give us -6. So that's -6 equals 0. So I can essentially say plus and minus would give me -6, right? So that means P -3 equals 0. So what is the charge or oxidation number of phosphorus here? +3. That's how you solve for oxidation number of each of the atoms present. Okay, follow the rules step by step. Let's try another example, which is H2PO4 minus. So I'm going to erase this part right here, and I'll move on to the next question. If you guys want, you can just solve it by yourself. You can pause the video right here and try to follow the rules step by step. So next I have H2PO4 minus. The first rule tells me, we go again, rules step by step. So the first rule was about free elements in their elemental form. That is not the case here. I don't have any of those. Then I go to the second rule, which says the charge oxidation state total charge is going to be equal to whatever the ionic charges, which I can apply here. So I can write down that whatever is the total oxidation state of hydrogen, 2 hydrogen, 1 phosphorus, and 4 oxygen is going to be total should be equal to the total charge. In this case, the charge is -1. So total should be equal to -1. And I'm solving for phosphorus here again. Now I go to next rule, which tells me that the oxidation number of oxygen is usually -2, unless it's a peroxide. I know this isn't a peroxide, so I can assume in this case that oxygen here, each oxygen is -2. So I know that right now. This oxygen is, I can write this as -2. Okay, what's the next rule? The next rule was about hydrogen. That the oxidation number of hydrogen would always be +1, except if it's a metal, if it's making a compound with one of the metals. In this case, that's not true. The exception is not true, I mean. So what would be the charge of hydrogen in this case? I can assume each hydrogen is always going to be +1. So I can assume this value is +1. So now I can solve for phosphorus. So let's solve for phosphorus. So each hydrogen is +1. I don't have to go to the next rule anymore. Plus phosphorus plus 4 times -2 equals -1. So if I solve for this, that gives me +2 plus phosphorus, and 4 times -2 would give me -8, and negative and positive would give me negative. So it's -8 equals -1, which means phosphorus -6 equals -1. So phosphorus would be -1 plus 6, which is equal to +5. So my final answer is the oxidation number of phosphorus in this case is +5. So remember, you cannot just assume phosphorus would be +3 based on the periodic table, because phosphorus belongs to the nitrogen family. Okay, so never solve, never just make assumptions. whatever is given to you, just follow the rules step by step, and once you have the rest of the values given to you, solve for the unknown value. Okay, don't keep on going by the rules and just come to like, oh, phosphorus is nitrogen family, so it's +3. Okay, so make sure you follow the rules step by step. So that's how you can identify what is the oxidation number for any element in a particular compound. Okay, moving on, the answer is right here. It's also solved for you. So now this is just showing you again an example of an oxidation reduction reaction. So if I come back to this reaction, this is an example of a redox reaction. What is happening here? Zinc is reacting with H ions to produce zinc ion, and hydrogen gas is released. Okay, so usually this hydrogen plus is coming from an acid, doesn't matter. There is a reactant which is giving us H plus ions. Okay, so now if I look, can I identify is this as a redox reaction or not? How can you identify what is the zinc is one of the reactant? What would be the product that zinc is giving us? Zinc is definitely getting converted to zinc 2 plus, and H plus is getting converted to hydrogen. So first identify your two half reactions. Okay, so these are my two half reactions. One is this, the other one is this. Now I don't know which one's what. So what is the oxidation number of zinc? We know zinc is a metal. Its elemental form, how it exists in nature, is essentially just Zn. This is a metal, it exists as Zn. So what would be the oxidation number of zinc? Our first rule of oxidation number tells us elemental form, the oxidation number would be 0. That's why you see a 0 right here. Okay, what is this getting converted to? This is getting converted to zinc 2 plus. That is our second rule. Our second rule tells us if you have an ion, the whatever is the charge on that particular ion by itself, that is its oxidation number. So oxidation number of zinc 2 plus here would be +2. So that's how I came up with this number. Okay, next I come back to my other compound, other reactant, which is H plus. Ignore this 2. This is the stoichiometric coefficient. What is our ion here? Ion is H plus. Again, this brings me to rule number 1 doesn't apply here. Rule number 2 applies here. Whatever is the charge on the ion by itself, here the atom is by itself. So the charge is +1, meaning its charge or oxidation number is going to be also +1. Getting converted to hydrogen. What is the oxidation number of hydrogen in hydrogen gas? Hydrogen gas is the elemental form of hydrogen. This is how it exists. So this brings me to rule number 1. Here hydrogen would have an oxidation number of 0. So now if you guys remember, what is the rule with oxidation number? Oxidation number increases when something is oxidized, right? So in this case, zinc oxidation number is changing from 0 to +2. So oxidation number is increasing from 0 to +2, meaning this is getting oxidized. So this is our oxidation reaction. Zinc is getting oxidized. What is happening to hydrogen here? H plus is getting converted to H2. Oxidation number is going from +1 to 0, meaning oxidation number is decreasing. A decrease in oxidation number happens when something is reduced. So this is a reduction reaction. So that's how you can identify which is oxidation and what is reduction. Okay. So in this case, oxidation is one reactant loses electron, reducing agent is oxidized, oxidation number is increasing. So all these three things tells you it's an oxidation. Oxidation number is increasing. So this is our reducing agent because this is getting oxidized, and it is losing electrons. We'll come back to how it's losing electrons. Electrons will always carry a negative charge, right? So this had a 0, and only way a reaction or a redox reaction happens is by exchange of electrons. Either electrons are lost or electrons are gained. Plus never changes. Okay, how do you get a plus charge? Plus charge is happening. Why? Because something is losing electrons. Okay, so you can never add any protons or neutrons to anything in an atom. Only thing that changes is number of electrons. So what is happening to zinc in this case? Zinc is changing from 0 to +2, meaning it is losing the electrons. That's why, because it lost the negatively charged electrons, its charge became positive. Okay. What happened to hydrogen here? It was going from +1 to 0, so it has accepted electrons, it has gained electrons. That's why its charge became from positive to 0. So always work in terms of electrons. You cannot add protons, you cannot remove protons. Only thing we can do is we can either add electrons or we can remove electrons. Okay, so that is how you can identify in this case which is the oxidation half, which is the reduction half. Okay, all of this that is written out right here will become more clear as we progress through the rest of the few slides. Okay, so let's move on. Going further, next step we are going to do is we are going to learn how to balance redox reactions. That's another rule by rule, step by step procedure. So these are some of the rules that you have to follow. Again, make sure you understand the rules, make sure we follow these rules. Do not skip any of these steps, okay? Go step by step. What is the first step? I'll just go over briefly what the steps are, and then we'll do an actual example with each step at a time. So first thing we have to do, if the question tells you balance a redox equation, write the skeletal equation for the oxidation and reduction half reaction. So one reaction is given to you, you have to first divide it into oxidation half and reduction half. So if you divide it into two different reactions, two half reaction, like we just saw in the previous example, what is getting oxidized, what is getting reduced, then you divide it into two reactions. Now balance each half reaction for all the elements except hydrogen and oxygen. So balance for all elements, leave hydrogen and oxygen alone. Once that is done, you move on to step number 3, which is balance each half reaction for oxygen. So balance all elements first, except hydrogen and oxygen. Then you balance oxygen. How can you balance oxygen? By adding water. So for every oxygen, you add one water. If there are two oxygen to balance, you add two water molecules. There's nothing else you can add, okay? If you want to balance oxygen, balance by adding water. Next step, once oxygen is balanced, balance each half reaction for hydrogen. How would you balance hydrogen? By adding protons. So H plus ion. Don't add anything else. Always balance all the hydrogens by adding H plus. Next, we can balance each half reaction for charge by adding electrons. Next thing you're going to do is balance the total number of charge on both the sides of the arrow by adding electrons. Again, remember you can only add stuff here. See, we are only adding water, add hydrogen by adding protons, and add electrons. You can never remove anything. Okay, so only thing you can do is add stuff to the reaction. If necessary, multiply one or both half reactions so that the number of electrons consumed in one is equal to number of electrons produced in the other. So when you write two reactions, you are going to balance the two reactions so that the number of electrons in both the reaction is same. So for instance, in one half, if I have 6 electrons, the other half should also have 6 electrons in total. Okay. Last step, you add the two reactions and just simplify the equation. That's it. That is your balanced equation. Now there are two more steps to balancing a redox equation. Now either the question will ask you balance an equation in acidic conditions, or it will say balance the equation in basic conditions. So if the question says in acidic, or if it doesn't tell you what condition, assume it is giving you acidic condition. Okay. If it does not give you what is the condition, assume it is acidic. Remember that. Okay. How do you balance the acidic equation? You stop right here, step number 7. That is your acidic condition. If the question asks you to balance it in basic conditions, that's when you go to rule number 8, step number 8. Step number 8 is, if the reaction takes place in basic medium, add hydroxide ions, the equation above obtained in step 7 to neutralize the protons. So whatever is the number of protons in your final equation after step number 7, add the same number of OH minus on both the sides of the equation. Okay, so add hydroxide ion in the equation obtained in step number 7 to neutralize all the proton ions on both the sides. Okay, remember acidic condition has protons, so that's good. But if your reaction is basic, you cannot have protons. So that's why whatever is the number of proton present, you add same number of hydroxide on both the side of the equation. Okay. Next, you will simplify it, and I'll show you how to simplify it step by step. Okay, so these are the rules. Let's actually do an example. So let's say this is our question. We are trying to balance this particular redox reaction in acidic condition. Okay, so I don't give you a condition, that means it's acidic. So the question is, can you balance this particular reaction? Okay, now I have written out the rules for you right here, but again, the rules won't be given to you in exam, so you should know these rules. What are the rules? Go step by step. First thing we have to do is we have to divide this reaction into two half reactions. Okay, so let's do that. I'm going to write with my black pen here. So first I have to identify what is oxidation and what is reduction half. Okay, or you don't even have to identify that, you just have to divide it into two half reaction. So how do you divide it into two half reaction? I know, we start with one, which is iron right here. Okay, so what is happening to iron? Iron would be changing to iron 3 plus, right? So identify your reactant and product, sorry. So this is my one half, iron is changing to iron 3 plus. The second half is Cr2O7 2 minus, which is in this case the chromium here, chromium atom is definitely changing to this, right? So the second half is this particular. So identify the element and just follow the element. That's it. So now let's write down two half of our reaction. I'll write one half right here, which is Fe2 plus is changing to Fe3 plus. Okay, and that's my one half. Now I'll write down my second half, which is Cr2O7 2 minus is changing to, I should have left some more space. Bad, let me rewrite this. Cr2O7 2 minus is changing to Cr3 plus. So that is my second half of the reaction. So the first step is write the skeletal equation for oxidation and reduction half reaction, which is this. Now you can either identify what is oxidizing and what is reducing, or you can just leave it like that. Okay, we can identify it later on. Next step is balance each half reaction for all steps except the hydrogens and oxygen. So let's do that. What is the other element here? Iron. Is it balanced? I have one here in the reactant, I have one in the product. So this side is balanced. The second half reaction is Cr2O7. There's Cr and there's oxygen. I'm not going to balance oxygen right now. I'm only going to focus on Cr. How many do I have on reactant side? 2. On product I have 1, which means I have to put a 2 right here. So let me make space for 2. I'll put this arrow right here, and then we are going to balance the chromium, number of chromium atoms. So this is 2. Okay, now balance each half reaction for oxygen. So this has no oxygen, so I'm going to leave it like this. This side has oxygen, so let's balance oxygen. How can you balance oxygen? By adding water. So let's do this step. I have 7 oxygen on the reactant side and 0 oxygen on the product side, which means I have to add 7 oxygens on this side, right? How do I add oxygen? Just by adding water. Each oxygen requires 1 water, so 7 oxygen would require 7 water molecules. There we go. Next we move on to step number 4. Balance each half reaction for hydrogen by adding proton. This half has no proton, so we can leave it like that. This side, let's balance the proton. How many protons do I have on reactant? None. Product, I have 7 times 2, 14 protons. So we are going to add 14 protons on the reactant side. Sorry, this is 14. Okay, 14 protons. Perfect. Now we balance step number 5. Balance each half reaction for the charge by adding electrons. Again, you can only add electrons, you cannot take off any charge. What is the total charge here on the reactant side? Total charge I have is +2. Total charge on the product is +3, which means I need, again, you can only add electrons here. Okay, so if I add electrons here, I'm going to add a negative charge. That would make a total charge of, it's going to reduce the charge, right? So always make the charge equal to the lower number of positive charge. Okay, so What is it lower charge here? My +2, +3. If I add one electron on the reactant side, that would give me that would allow me to balance the charge, right? So let's add electrons on the reactant side. Again, remember you can only add electrons. So if I add, this is +2, this is +3, I can make the charge, I can only make it equal to lower charge. So in order to make this +3 equal to +2, what do I need? I need one extra electron. So if I add right here, one electron. What is the total charge now? The total charge now is -1 +3, that is +2. So both the charges are equal. Now my reaction on this half is balanced. Okay, so I'm going to erase this. Okay, so now we'll come back to our second half of the other reaction, the second reaction, second half. We'll try to balance the charges right here. Again, remember we want to bring the charges to the lowest number of charge that can be present because we only add electrons. So let's see what we can do here. What do I have? What is the total charge on reactant side? I have 14 plus, so plus 14, right? So how did I get that? 14 times each hydrogen plus I have this -2 of this whole thing, and I just have one of those, so that gives me a total positive charge of plus 12. What about the reactant side? We have 2 chromium, so 2 times plus 3, each of them is plus 3, plus 7 of water. Water is neutral, so that is 7 times 0, which means a total charge of plus 6. Can I make both the sides equal to plus 12? I can't, because then I'll have to add something positive here, which I don't have. So I'll have to make both the sides equal to plus 6. How can I make it equal to plus 6? If I add 6 electrons on this side, okay, let's add, if I add 6 electrons, 6 E negative on this side, that would make a total charge of now 6 electrons, so 6 times -1, each electron is -1 plus, which was already 12, that gives you a total charge of plus 6, which is equal on both the sides now. So these are my two half reactions now. One is this, the other one is this. I'm done with balancing electrons. Step number 5, perfect. So now we move on to step number 6. If necessary, multiply one or both half reactions so that the total number of electron consumed in one is equal to the number of electron produced in the other. So what does this step mean? What is the total number of electrons in this case that is going on, used or produced? 1 electron. Okay, so this half is only 1 electron. This half has 6 electrons. So you can see here electrons are being lost in this reaction. If electrons are being lost, Leo, so this is Leo, loss of electrons, so this is our oxidation half. That's how you can identify what's happening here. Electrons are being used up, so gain of electrons. So this is GER, meaning this is reduction half. So first thing we did here is we identify what is oxidation reduction. Now the step actually is the number of electrons gained by one and lost by the other should be equal to each other. Now again, we can only increase the number ever. We can only add stuff. We cannot reduce stuff. So if this is 6 electrons, how can I make this 6? I can multiply the whole reaction by 6. That would make this 6 electrons. Okay, so make sure you multiply the whole reaction by 6 and not just the electrons. You cannot do that. We have to multiply the whole reaction by 6, which means now I will have two half reactions. Let's rewrite our two half reactions. So I'm going to erase this portion right here because we have gone through this. Okay, doesn't mean that you don't have to. I'm just erasing it for me to get some more space. Okay, so I'm going to rewrite all my reactions now in this space. What is the first half reaction? Just multiply by 6. So I have 6 Fe2 plus produces 6 electrons, 6 times 1 plus 6 Fe3 plus. So that's my first half. Let's write our second half. We did not multiply this with anything, so it stays as is, which is 6 electrons plus 14 protons plus Cr2O7. 2 minus is changing to 2 Cr3 plus 7 water molecules. So that's my second half. What is the last step? Add the two half reaction and simplify. Simplify means if you have to cut anything, divide by anything, do that. First, let's add our reaction. To add, remember whatever, if you have the same thing on the reactant side and the product side, they will cancel out. Okay, so what do I have on reactant side? 6 Fe2 plus. Is there any Fe2 plus anywhere else? No. So we will rewrite 6. Let me write the final answer in black. 6 Fe2 plus. That's my first reactant. Any other reactant here? No. So we move on to second. The second reactant here is 6 electrons. Are there electrons anywhere else in any of these other reaction? Yes, there are 6 electrons here. So 6 electrons are being used up. 6 electrons are being produced in the first half, meaning I can cancel these electrons. So if there's something that is as a reactant and product, you can cancel those out, right? That's how you add reactions. So we cancel these electrons. Next reactant is 14 protons. So plus 14 protons. Last reactant is Cr2O7, nowhere else. So plus 1 Cr2O7 to negative. Okay, that's all our reactants covered. Produces. Now go to products. We have 6 Fe3 plus. Anywhere else? No. So 6 Fe3 plus. 2 Cr3 plus, nowhere else. So 2 Cr3 plus. 7 water, nowhere else. So 7 water. That's our complete overall reaction. We just have to put the phases now. So remember, all the ions will always be aqueous. If something is in elemental form, that's the only time when you will decide if it's a metal, it's going to be solid. If it's a gas, you're going to put gas. But otherwise, if it's ionic, everything will be aqueous. If it is water, it's always going to be liquid. Okay. So that is our final answer for balanced chemical reaction. And that is if the two half reactions are done in acidic conditions. If the question doesn't tell you anything, you assume it's acidic. So that's how I know my acidic half complete reaction balanced redox reaction would look like this. So those are the steps. Follow step by step. It's fairly simple. It looks very complicated, but if you follow these steps, it's going to be done, completed by the end. Okay. Now let's extend this question. Now if I ask you what would happen, what would be a balanced reaction in basic medium? Okay, so how would you identify in basic? First thing, you have to repeat all this, what we just did, and you come up with this as your final answer. Sorry, not the final answer. You come up with this step. This is your step number 7. Now, if the question has basic medium in it, then you move on to step number 8. So let's do step number 8 now. Yeah, I just rearranged the slide. So we have more space to move on to the next step. Okay, so now let me change the color right here. So if I'm moving to the next step, and the question is, can you do this in basic conditions? So first thing is you will do all the steps that we just did and come up with this reaction, which is step number 7. The step number 8 tells you for basic medium, add hydroxide ions to both the side of the equation, which is equal to number of hydronium ions. So how many protons do I have here? H plus. Whatever is the number of total H plus, you add same number of OH minus on both the sides. So I have 14 H plus on this side. So I'm going to add 14 OH minus on both the sides. Okay, now what happens when you add OH minus? Remember, you're adding it to both the sides. Okay, so once you add it to both the sides of the reaction, now we'll add these two reactions. What happens when an H plus reacts with, if an H plus reacts with OH minus, it is going to produce water. Okay, so one H plus ion with another OH minus ion produces one water, H OH, H2O. Okay, two hydrogen ions and one oxygen. Okay, so this essentially means on this side now I have how many water? These two will react to produce 14 water on the reactant side. What happens on the product side? On product side, I already have 7 water molecules. Now you cannot have the same compound as a reactant and a product, right? So we now will have to cancel the amount of water. The 7 water in this side, 14 on the reactant side, meaning in total I can cancel these 7 water and subtract those from this side. That would give you a total of 7 water on the reactant side. So 14 minus these 7 would give you 7 water on reactant. So what happened to your final reaction under basic condition? Now we rewrite this equation. That's going to be 6Fe2 plus, which is aqueous, plus this is cancelled, right? This and this reacted to give us this, and then this got cancelled with that to give us finally 7 water. So I have 7 water liquid, 1 Cr2O7, 2 minus, again an ion, so aqueous, produces 6Fe, 3 plus, plus 2 Cr, 3 minus, no water, but what did we add now? We added these 14 hydroxide ions, so 14 OH minus. So this would be a final answer if the reaction was to be balanced under basic, medium, or in basic conditions. Okay, so remember, what did we change? The major difference between acidic and basic is in acidic you would have protons. In basic conditions there is no protons. Only thing you will have at the end would be hydroxide. That's the only difference. So add OH minus, same number of OH minus as the proton on both the sides, then cancel the protons to form water, and then balance the number of water molecules. That's your final answer. That's how you balance a chemical reaction, a chemical redox reaction, right? Okay, now let's do one more example. I'll follow these steps. This time I'll try to be a little bit faster. This was too much detail, so we'll try to go a little bit faster this time, okay? But again, remember these are the steps. That's what you have to memorize. So it's not a lot to memorize. First step, divide the reaction into two halves. Then balance all the elements except hydrogen and oxygen. Next, balance oxygen by adding water. Then balance hydrogen by adding proton. Then balance charge with electrons. And then you combine the two reactions if needed and balance the total number of electrons in both the reaction to be same, add, and then simplify. Okay? And if it's in basic condition, you add hydroxide ion on both the side of the reaction and then simplify. Okay, so two reaction, then hydrogen, oxygen, all the elements except hydrogen, oxygen, then hydrogen, then charge, and then balance. Make sure the number of electrons are same in both. Let's try one more question. I have this in the slide right here, which is all the steps what I just showed you written out as well. Okay, so this is in acidic and basic conditions. So this is the reaction in basic condition. So now we'll move on to the next example. Let's try and quickly solve this question this time. So here are my two half reactions. Okay, let's first, here's my complete redox reaction. We just have to balance this ionic equation. How can we balance it? First, we have to divide it into two steps. So remember, what is one of the compounds here is CrO7 and I minus. What is it giving us? It's giving us Cr3 plus and I2. So I know definitely I minus is changing to I2. So that would be one reaction. And Cr2O7, 2 minus is changing to Cr3 plus. So that's my other half. So let's write our two half reaction. First is I minus is changing to I2. The second is Cr2O7, 2 minus is changing to Cr3 plus. Okay, This is again, if it's ions, ions are always aqueous, and if it is something else, you would be able to write down it as solid, gas, whatever is needed. Okay, so in this case, it tells us I2 is solid. These are my two halves. Let's start balancing them. How can we balance it? First rule is divide it into two halves. Then the second rule is balance all the elements except oxygen and hydrogen. The other element is iodine. How many I have on the reactant here? 1, 2, which means I cannot reduce it. Okay, you can only add stuff. So I'll put a 2 right here. Okay, let me put a 2 like this so it's clearer. So I have 2 iodine right here. Okay, let's balance the other stuff here. I have oxygen. I'm not going to touch it. Next is chromium. I have 2 chromium here, 1 here, which means I have to put a 2 right in front of this. Again, only thing you can add is a stoichiometric coefficient. Okay, you can only add this in front. You can never change the subscripts of anything. That's how you balance chemical reactions, right? Okay, next step. Balance, what was the next step? Next step was balance oxygen by adding water. Is there any oxygen here? No. Oxygen here? Yes. I have 7 oxygen, so I will add 7 water molecules to balance it out on the other side. Again, water is liquid, so let's put liquid. Next step, balance the hydrogen atoms by adding protons. Are there any hydrogen on this side? No. Are there hydrogens on this side? Yes. How many on the reactant? 0. How many on the product? 14. So I will have to add 14 protons on the reactant side, which is 14 H plus. Perfect. Next, balance the number of charge by adding electrons. So what is the charge on this side? The total charge here is 2 times -1, right? So 2 times each of them is -1, which means a total charge of -2. What is the total charge on the product side? It is 0, right? It has no charge here. Nothing on the right superscript means the charge is 0. So what can I do? Again, you make it equal to the least amount of charge. If you add electrons on this side, it's going to increase the negative charge. But I want to charge to be equal to each other. So only thing I can do here is I add electrons on this side. So if I add electrons on the reactant, sorry, on the product side, how many? 2? That would make this total charge of 0 plus 2 of -1, which gives you a total charge of -2 again. So I added, sorry, let me stick to my symbol, which is 2 electrons. So I added 2 electrons. Okay, now that balances my first half of the reaction, one of the half of the reaction. Now let's balance the second half of the reaction with number of electrons, the total charge. So what is the total charge on the reactant side as of now? As of now, I have 14 protons, so 14 times each is +1. So 14 times +1 plus 1 of the -2, so that's a total of -2, which would give you 14 minus 2, which is a total of 12. On the other side, on the product side, I have 2 times +3 plus 7 times 0, because it's a neutral compound, which gives you a total of +6. Now again, remember, you can only add electrons. Adding electrons will reduce the total charge, right? If I add electrons here, it's going to reduce this charge, which is not going to make it equal to 12. So you can always make it equal to the least charge. So I can add electrons on this side. How many electrons should I add to 12 to make it equal to 6? 6 more electrons. So I will add 6 electrons on the reactant side. That would make a total charge. If I take now total charge of everything, that would be 6 of -1 plus this total side was 12. That gives you a total of +6. So this is also +6, this is also +6. Perfect. Step number, whatever step this was, is done. Next we move on to step number, I believe it's 7. um, no, step number 6. It tells us that we have to balance out, make sure whatever is the electron lost by one reaction is the electron gained by the other reaction. So The first half, what is happening here? Electrons are being lost. It's product, so electrons are being lost, meaning this is an example of what kind of reaction? Loss of electrons. So this is LEO. So this is oxidation half of our reaction. On the other side, we have electrons are being added up, so they are gained. So this is, sorry, GER, GER. This is reduction half of our reaction. Okay, so now we have to balance the total electrons. How many electrons do I have here? I only have 2 on one reaction and 6 on the other reaction. Again, you cannot remove anything. You can only add stuff. So I cannot reduce the 6, but I can increase the 2 to 6. How? By multiplying the complete reaction by 3. Now remember, you're multiplying everything by 3, each reactant and product. So let's rewrite our first half of the reaction, or the oxidation half. So this is my oxidation half. What would it be? It will be equal to 3 times 2 gives you 6 I minus. Again, this is aqueous. Will produce how many? 3 times 1, 3 iodine. This is a solid, plus 3 times 2, 6 electrons. So that's my one half. Now I come to the second half, which is reduction half, which is this. What do I have? I have 6 electrons plus 14 protons plus Cr2O7, 2 minus is changing to 2Cr3 plus 7 water. Now we add everything up together. So let's add it. First reactant is 6 iodine. How many iodine? Are there anywhere else? Iodide ions, nowhere else. So I write 6 I minus. Again, this is ion, so it's aqueous. Then I have 6 electrons. Are there anywhere else electrons? Here. This is on reactant, that's on product, so they'll cancel each other out. Perfect. Next I have protons on the reactant side. Are there protons anywhere else? No, so that gives me 14 protons. Again, this is also ion, so it's going to be aqueous. Next I have 1 Cr2O7, 2 minus. So 1 Cr2O7, 2 minus. This is also aqueous since it's ionic. Produces 3 iodine. Are there anywhere else? No. So 3 iodine, which is a solid. 2 Cr, 3 plus. Anywhere else? No. So plus 2 Cr, 3 plus. These are Cr ions, and ion makes it aqueous. Next I have 7 water. Anywhere else? Nope. So that is 7 water, and water is always liquid. So that is my final balanced redox reaction in this case. And the question is asking acidic, so I can leave this right here. That's my final answer. Okay. Again, everything's done for you in steps. Okay, last question is permanganate ion reacts in basic solution. Okay, so make sure you read the question, just don't jump to it. Permanganate ion reacts in basic solution. So this is basic with oxalate ion. This is permanganate, this is oxalate to form carbonate, which is CO3 2 minus, and solid manganese dioxide. Balance the skeleton ionic equation for the reaction between this and this, sodium permanganate and sodium oxalate in basic solution. So now we have to balance this out. You can pause the video right here and try to balance it out by yourself, and we'll also give it a try. Okay, so I'm going to pause. You can pause the video right here if you want to try it out by yourself, and then you can come back and look for answer. Okay, let's begin. So let's identify what the two halves would be. This is Mn, so Mn is going to produce something with Mn, which is right here. This is carbon. Carbon is going to produce something with carbon, which is right here. Perfect. So let's write down my skeletal halves first, which is, should leave some space just in case if I need. So MnO4 minus, and we can identify the ions later on, so don't worry about it, produces what? MnO2. That's my first half. And then I move on to my second half, which is C2O4 2 minus is changing to CO3 2 minus. Okay. So let's start balancing this out. We'll go again rule by rule. Rule number 1 is separate them. Done. Rule number 2 is balance everything except oxygen and hydrogen. So forget oxygen. What do I have here? 1 Mn, 1 Mn. Balanced. Okay. Second reaction. Forget oxygen. How many carbon? 2 here and 1 here, which means I need a 2. If this would let me write, I need a 2 right here. So that's my second step done. Third step, balance oxygen by adding water. So how many oxygen here? 4. How many oxygen here? 2, which means I need 2 extra oxygen on this side. How will I add that? By adding to each oxygen. Remember, each oxygen you need 1 water molecule. So 2 oxygen, I need 2 water molecules. Perfect. Next, I come back to second reaction, which is 4 oxygen right here, and how many oxygen on this side? 6 oxygen. 2 times 3, so I have 6 on this side, 4 on this side. Again, I can only add, so I have to add 2 oxygen on this side, meaning I will add those by adding 2 water molecules right here to water. Okay, what is the next step? After adding oxygen, you balance hydrogen. How many hydrogens here? None. How many hydrogen on this side? 4. So I will add. How do you balance hydrogen? By adding proton. So I'll add 4 proton on the reactant side. Coming to the second reaction, I have 4 hydrogen on this side, none on this side. So again, I will add 4 hydrogen ions on that reaction as well. Okay. Next, we move on to the next step, which is balancing the total number of charge by adding electrons. So let's first figure out what is the charge on this side. Well, the first half, the total charge here is 4 protons, so 4 times plus 1 manganese, which is -1, which give you a total of 4 -1, which is plus 3. How about the other end? The other side is, this is neutral, right? So it is 0. Plus this is also neutral, so this is 0. So that's a total charge of 0. So now again, you have to bring it down to the equal to least charge on both the sides. What is the least one? Equal to 0. So I have to reduce this 3 to 0. How can I do that? By adding 3 electrons on this side. So let's add 3 electrons right here. Okay, which means what is my total charge on this now? It's 3 times -1 plus whatever the total charge here was, which was plus 3. That gives you a total of 0, which is equal. Perfect. Next, I move on to this reaction, balance my charge. What's the total charge on this side? 2 water, so 2 times 0, water is neutral. 1 oxalate ion, which is 1 times -2. So that gives you a total charge of -2. How about the other side? The product side, I have 2 carbonate ions, so each carbonate is -2. Right? Plus 4 proton, which is 4 times plus 1. So that gives you a total charge of -4 plus 4, which is equal to 0. So again, you bring it down to equal to least. Which side is least? This is 0, this is -2. The smaller value here is -2. So I have to make both the sides equal to -2. How can I do that? By adding 2 electrons on the product side. So now what is the total charge now? 0 for this part plus 2 -1, which gives you a total of -2, which is equal to each other. Again, remember, a lot of times students make mistake. They want to make the charge equal to 0. Okay, that's not true. You want both the side to be equal to whatever the charge is. So if this is -2, you want the other side also to be -2. Okay, don't try to make the charges equal to 0. You won't be able to balance it, because only way you can balance the charges by adding electrons. So if you add 2 electrons here, that would make it 2 minus from here plus 2 another electrons, that would make it a total charge of -4. Okay, so you won't be able to ever balance it. Okay, so now that I have my charges balanced, what's the next step? The next step is that we want to make sure that the total number of electrons lost by one reaction and gained by the other reaction is equal. So let's balance the electrons now. Okay, so what is happening in this half of the reaction? There is electrons are the reactants. So the gain of electron, the electrons are being gained, which means this is GER. So this is my reduction half now. What is happening on this side? Electrons are being lost. It's a product. So they are being lost, they are being produced. Lost means LEO. So this is oxidation half of my reaction. So first I've identified that. Next step, what do we do? To balance electron, how many electrons do I have in this reaction? I have 3 electrons here and 2 electrons here. How can you balance the electron? You can do that only by, if I multiply this side of the reaction by 2, that would give me a total number of electrons as 6. And if I multiply this other oxidation reaction by 3, I'll write it right here. If I multiply that 3, that would also give me a total number of electrons as 6, right? That's the only way we can have electrons balanced out. So perfect. Let's rewrite our balanced 2 half of the reaction, which would be everything here multiplied by 2. So 2 times 3 would give us 6 electrons, plus 2 times 4 is 8. So 8 protons. 2 times MnO4, so 2 MnO4 minus, which is permanganate ion. Don't forget these charges. Make sure you're carrying over your charges. Produces what? 2 MnO2, and 2 times 2 is 4 water. Moving on next to the second half. This is again my reduction reaction. Now I go to the oxidation reaction, which is this. This I'm doing multiplying by 3. So 2 times 3 is 6 water, plus 3 times 1 oxalate ion would give you 3 C2O4 2 minus, produces what? 2 carbonates, so 2 times 3 gives you 6 CO3, and each of them is 2 minus, plus 3 times 4 is 12 protons, plus 3 times 2 is 6 electrons. Alright, so now the last step, actually not the last, the next step is we add the 2 reactions. So how do we add the 2 reaction? Go step by step. What do I have? I'll do this in red. I have 6 electrons. Are there electrons on the other reaction? Yes. This is reactant and this is product, so they cancel each other out. Next, I have 8 protons. On the reactant side, do I have protons on anywhere else? Yes, I have protons right here, which is 12. So these 8 and this 12 will cancel each other out, right? So this 8 would cancel. What would I be left with? I would be left with 12 minus 8. Right. So 12 minus 8 would give me finally 4 protons here. Okay, so that's also cancelled out. I don't have a reactant yet. Next, I have MnO4 minus. Do I have anywhere MnO4 minus? No. So I'll just rewrite this. So it is 2 MnO4 minus. Next, I have water. I have 6 water on this side. Anywhere else do I see water? Yes, there's another water right here. This is 6, this is 4. So they will cancel each other out because one is on the reactant, one is on product. If they were on both were on the same side, you would add those up. But because they are on opposite sides, you will be subtracting those out, right? So 6 minus 4 would give you a total of 2, right? So that would give me 2 water molecules. Again, this is aqueous, water is liquid. Okay. Next, I have next reactant oxalate. Is there anywhere else present? No. So I write my oxalate right here. So C2O4 2 minus. Perfect. That's my reactants covered. Let's move on to product. How many products? MnO2. Anywhere else? No. So that is going to be 2 MnO2. This is, remember, it gave you in the reaction it was solid, so this is going to be solid, plus next product is carbonate ion. Anywhere else? No, so that would be total of 6 CO3, 2 minus. Anything else that's left? Remember, we left this right here, so don't forget about this. Okay, you canceled it out, but we did not write it yet, so it's going to be 4 protons left here. Protons again are ions, so it's going to be aqueous. And if any other phases you forgot, rewrite those. So this is aqueous, and oxalate is also ion, so this is aqueous. Perfect. That's step number 7. Do we end right here? No. Why? Because the question was in basic solution. So we move on to next step, which is when it is basic, what do? We balance the reaction with total number of hydroxide ion. How many hydroxides are here? How many protons are here? 4. So which means I will be adding 4 hydroxide ion to both the sides. So let's add 4 hydroxide ions. So if I add 4 OH minus right here and 4 OH minus ion right here, okay, I am little low on space. So 4 hydroxide ions on both the sides, which means this hydroxide will stay as is. This is the water. Perfect. What happened to these protons? They will react. These two will react with each other to produce 4 water molecules. Okay. If I have 4 water molecules here, do I have any water molecules on the other side? I already have 2 on this side. Now you cannot have same reactant and product side, same compound, which means I'll have to cancel out water now. So which means this has 4, this has 2, so this has to go away. It's going to be 4 minus 2, a total of 2 water molecules on this side. So what would be a reaction? I don't want to rewrite this, but you do. You should rewrite it in your final answer. Let's rewrite it as my final answer. It's fine. I have space. So I have 4. My final answer would be 4 hydroxide ion, aqueous, plus 2. Oh, sorry. This is going to look a little rough because I'm really trying to make the most out of this space. This already cancelled out. Plus 3 C2O4, 2 minus ions will produce what? 2 MnO2, which is solid, plus I'm going to leave this right here, 2 water molecules, and this, which is 6 carbonate ions. Okay, this water will be liquid, and this is what your final answer should look like. So make sure you give me this as your final answer. It's a lot of steps, but the steps are fairly easy. I'm trying to explain you step by step, that's why it's taking this long, but if you try to do it by yourself, it's going to be fairly simple. All right, so that is how you balance your final reactions. That's all. The answers are also solved for you right here. Pretty and step by step, so you should be able to identify what your final answer is and how you can get to this following the steps that are shown right here. Okay, so we just confirmed this was our final answer, so everything comes down to this. So make sure you give me this as your final answer, and don't forget to include the phases during your reaction. Okay, so that's about balancing a chemical reaction. This was all about the first part of electrochemistry, which was how to identify what is the oxidation number and how to balance a chemical reaction. So if you want, you can take a pause right here, because next I'm going to start with the next concept. Okay, so if you want, just take a pause right here and you can come back to the video for the next concept later on whenever you have more energy. Okay.